Hello there and welcome to the series The Basics of Embedded Audio Programming. I am Renato from Guitars AI, and today we're going to see how to configure and use LEDs, switch buttons, and the OLED display in this board. So let's get started. The C5515 EZDSB USB stick has 5 light emitting diodes, LEDs, and there are 4 of them. They're green, red, yellow, and blue. They're connected to some GPIOs, and one is connected to a special pin called the XF. So this green LED, the S1, is a fast general purpose output bit and is directly connected to the XF pin, and we can use these instructions to clear and set this. We've seen this before. So here I am in the Code Composer Studio. This is our Hello World project, and we use this instruction to set the LED off. And here we can see the schematics. So we have this pin XF and we have this LED green connected to it, and we use these instructions to turn it on and off. The 4 other LEDs are connected to GPIOs. So GPIO is a general purpose input or output, so it's a type of pin found on an integrated circuit that does not have any specific function. So the function of the GPIO pin is customizable and can be controlled by software. So you can set a GPIO to be input or output, and some GPIO pins may directly support protocols like serial communication and PWM and PCM. So, and it's typically a digital input, so they can only have support. They only support high or low on or off levels. So here is the schematics of the LEDs connected to the GPIO of the C5515 EZDSP. So we have GPIO from 14 to 17, and then we have our LEDs. And here also we can see the GPIO 14 to 17. So we have this. This is our microprocessor. So the GPIO peripheral on this C5515 provides general purpose pins that can be configured as inputs or outputs. So this is the GPIO. When configured as an output, then you can write to an internal register to control the state driven on the output pin. When configured as an input, you can detect the state of the input. So there is 16-bit general purpose IOs that can be individually programmed as input or output with some interrupt capability. This device uses 2 registers for controlling whether the GPIO is set as a general purpose input or output. So there's the GPIO direction registers, so IO-DIR1 and IO-DIR2. So writing 1 to those bits configures the pin as an output, and writing 0 configures the pin as an input. So this device includes 2 registers for writing the GPIO pins when they are configured as outputs. So the data out registers, so IO out data 1 and IO out data 2, they are used to change the state of the corresponding GPIO pin. So we have here all the registers that are related to the GPIO. They have their hexadecimal address range, and here we have the acronym for the for these registers. In our example, we are going to use these functions from this file here to set the direction of the GPIO. So we pass the number of the GPIO and the direction. So here it will detect which register to write, if it's DIR 0 or DIR 1, and then it will set if it's if the GPIO should be an input or if it should be an output. And we can also, if it's an output, we can set the output to be a 0 or a 1. So it's the same principle. We pass the number of the GPIO, and we set if it should be 0 or if it should be 1. So I'm here on Code Composer Studio, and I am inside this file that we are going to use in our example. So this is a function to initialize the LEDs. So we are using this GPIO set direction. We give the number of the GPIO. Here we have the GPIO out. So the GPIO to be out, it's declared as a 1 and in as a 0. Then if we go to see, we see this GPIO set direction, what we've seen before. So it's a number, it will check the bank ID. Depending on the bank ID, it will write on the register 0 or 1, and we have here the register is defined. We are going to talk about this volatile I/O port this later, but this is we're passing some addresses of the register. And here the GPIO in, it's a 0 if it's an in, and 1 if it's an output. So this way here we can set the direction of the GPIO, and we also have this set output. The principle is the same. It will check the bank, so which register we are going to write, and it's also here. So these are the, according to that table, what we've seen before. Here we have to set the either 0 to low and 1 to high, and this way we can set the GPIO output. The C5515EZ-DSP USB stick has two push button switches. They are connected to a port called GPIN1, and here is the circuit describing how these switch push buttons are connected. And they are not connected to a GPIO, but they are connected to a successive approximation analog to digital converter. So this is a kind of ADC that uses a series of comparisons to determine each bit of the converted result. You can read more about the successive approximation ADCs, and there is the successive approximation registers in the C5515. So the device includes a 10-bit successive approximation register ADC using the switched capacitor architecture that converts an analog input signal to a digital value at the maximum rate of the 62.5 kilosamples per second for use by the DSP. And the way we're going to detect is when you read, we have different voltage levels depending on which switches are closed. So if switch 1 is closed, we have approximately 1.5 volts. If switch 2 is closed, we have approximately 0.9 volts, and if both are closed, we have approximately 0.72 volts. So with these combinations, we can detect if the switch 1 is pressed, if switch 2 is pressed, or if both of the switches are pressed. So before we start reading push buttons values, it's important to talk about push buttons debounce. So the mechanical characteristic of push buttons makes this problem, this kind of noise, that when two contacts of the switch hit together, they tend to bounce off of each other a few times before settling down. So most mechanical switches has this bounce problem. There are many ways to deal with this problem, and we can also use some software debouncing techniques to minimize this problem. To read the push buttons from the C5515 board, we are going to use this function here. It's in this file. So basically we have some values for switch 1, switch 2, and both switches, and no key. So we define that this is based on these voltage levels I explained before, and then we will have a counter. The timeout is 10 milliseconds, so that we will give a 10 milliseconds for this debouncing, and we will read values, and we will put these values in a buffer, and we will compare the values between buffers, and if the values don't change, we can say that the value is stable, and we can use this value. So here we have these buffers. We have here we check the value of switch 1 with some tolerance, and if the value is in between this interval, the value is equal to switch 1, so we know that switch 1 was pressed. Otherwise, when we read the values from this ADC and it's in between this interval, so it means that it's switch 2 is pressed, and here this interval means that both switches are pressed, and this is when no switches are pressed. And we are comparing also here this buffer, and we update with the debounced new input in case that the last three values are identical. And if not, the switches they changed, but they were not debounced, and we'll wait for this debounce time, 10 milliseconds to pass, and then we will read again. So this is how we will return, for example, 3 states. So if no key is pressed, we will return 0. If switch 1 is pressed, we will return 1. If switch 2 is pressed, we will return 2. And if both switches are pressed, we will return 3. So this is how we're going to read our push buttons. So I'm here back in the Code Composer Studio. We're inside this file, and I'm looking at this function I've just described. So we have here at the SAR header, we have the definitions for the values of switch 1, switch 2, switch 1, 2, no key. So their values will be compared with these defined values here, and then we will define which switch were pressed. We also have this timeout for debouncing, which is also defined here, and it's related to the sampling frequency. So if we change the sampling frequency somewhere in our project, we need to make sure that everything is synchronized and we are using the same values. So the rest of the function goes as I just explained. We compare if the value is inside some intervals, accounting for some tolerance, and we also account for debouncing, and then we will return a value. So it's from 0 to 3. 0 is no key, 1 is switch 1, 2 is switch 2, and 3 is switch 1 and 2. So with this we can read from the push button, and we will know which switch were pressed. The C5515 EZDSP USB port has also an OLED, an organic light emitting diode. So similar to a liquid crystal display, LCD, and we can see here in these schematics that we have the OLED here. It's this OSD9616 model, and we have this power circuit that is enabled by the GPIO 12 from the microprocessor, and then we have also the communication of the I2C bus. So it's a 96 by 16 dot matrix. We are using the I2C bus address 03C. You'll find this on this datasheet of the EZDSP. But the problem is we don't have any information about this OLED. I couldn't find anywhere a datasheet. I couldn't find anywhere any information about this. So I am pretty much stuck with the examples that comes with the EZDSP board, and with some examples from Texas Instruments, and I can use some information from another OLED, the SSD1306, and try to figure out how to use this OLED here. So the SSD1306, it uses a bitmap static RAM holding the bit pattern to be displayed. In our case, we are using another OLED, so hopefully it's the same principle as the SSD. In our case, we have a 96 times 16 bits, and the RAM is divided in two pages. Page 0 bits from 0 to 8, and page 1 is bits from 8 to 16, and they are used for monochrome 96 times 16 dot matrix display. In this case here, this is the SSD 1306, and it has 128 by 64. So we have the bits from 0 to 63 and the segments from 0 to 128. So we just need to adapt to our case. We will have from 0 to 16, 0 to 15, and pages 0 and page 1. So we can demonstrate here how we can create an A, capital A letter. So imagine we are in page 2 on this, it can be any page. Then we have here the segments, so from 0 to 96 in our case. And then we have here 8 bits, so from bit 0 to 7. And if we set some bits to 1 and some to 0, we can create different letters and different shapes. So the idea is that we will use 96 segments, and we will use two pages, page 0 and page 1, and we can, for example, have two lines of written text, each line having 8 bits in height. So we have a total of 16 bits, and then we can also use 96 segments. So what we are going to do is that the easy DSP examples comes with a very limited implemented characters. So I will try to get some OLED fonts. So the SSD 1306 have some fonts that we can use just with some adaptation. So I'm going to try to keep it compatible to the examples that comes with the board and the examples by Texas Instruments. So I will try just to have minimal changes and to keep things compatible. But this is the idea. We have these pages and we have the segments, and then we can set bits to 0 and 1 and create different shapes. So instead of making all these drawings manually and creating our own font, I found on this GitHub from the SSD 1306 many different fonts of different sizes, and I decided to use this one. This LCD is 5 by 7, so it means that we have 5 values here, and it's representing 7, so there's a space of 1 bit. There are many different ways how we can define these fonts. There are with fixed width, what is this case here, so all the letters have the same width, but you can also have variable width, and then you need to use a different approach. I just changed the type of this variable for this ASCII set, so to keep it compatible with the examples from Texas Instruments. And we see here we have different we have numbers, some symbols, capital letters, small letters, and this is what I'm going to use. So the OLED is connected with the DSP processor through the I2C bus. We've seen this before, and in this file here we have this send function that will send commands, I2C commands. So this address is we've seen this before. We can find it on the datasheet of the USB stick board, and it's similar to how we used before to configure the audio codec. We are going to use this function to send commands, I2C commands, to the OLED. Then we also have this initialization file for the OLED. So the OLED, it has a lot of possible configurations. So we also have to initialize the I2C bus. Here is to power up. So as I mentioned, the OLED is connected to a power circuit that it's enabled by a GPIO from the processor. So we need to enable this GPIO to give power to the OLED, and we are doing this here. Then we are initializing the display. We need to set the start lines, set the contrast levels. This is remap is something really interesting, because we can remap, so we can invert, for example, this can go from 0 to 127 or from 127 to 0, so it's useful to invert rows and columns, so horizontally and vertically. That can be very useful. And we have here we can set offsets. We need to set clock, we need to set some voltage levels. Then we can also need to set the column addresses, the page. So this is the initialization of the OLED. So now we have a function to send commands to the OLED. We've seen this before. This is based on the I2C. We use this a lot to configure the OLED. And now we also need to have some functions to print messages. So we will have this function in this file is the print character. So I am counting here that we have a 5x7, so I am going to use extra space, so it will be a 6x7. In fact, it would be a 6x8, so we have 16 as a 96 by 16, so we will have 2 rows, each one with 8 bits, and we will have 96. So if I'm using 6, so this will give us the number of values of characters we can display in each line of the OLED. So here what I'm doing is I am sending, so this is values that will come from the font we have here, so those values here. So if I give it an A, it should send these values here. So this is what we are doing here, and an extra space, so there is space between fonts. So with this function to print characters, we can also have a function to print some messages. So we have a group of characters. In our case, we are going to use 16 groups of 16. So it will go, if we pass these values, like some text, and then it will go through each of the character, and then it will look into this table of the ASCII set, which is this font, what we have here. So this, it will look these values. We need to take in consideration that the first value starts here, so we have 0, 1, 2, 3, 4, 5, 6. So, and then this is what we are doing here. We are accounting for the 6. We also need to account for this 32 non-printable ASCII values. So when we are accounting for that, and then as we are using this 0, 1, 2, 3, 4, 5, and then we are multiplying by 5 here. In this way, we have this. We print the characters from this message that we want, and then we can also display this message. So from here we're just getting the characters from, for example, a string of characters. So we have a string with some text, and then we go through the characters, and then we look in this font table, and we get the values, and then we can send these values to the OLED. For that, we have this OLED display. message. So in fact I modified here, so it's the 5x7. So this way you have the original OLED display message that you can use with the examples that comes with the board, or we can use this one and use with the font that I included in this project. So here we can configure scrolling, so it's possible to have vertical and horizontal scrolling of text. We need to set the low and high column addresses, set the page. So we are setting the page 0, and this is the top line. So we will pass a top line and a bottom line to this function. So there's some text on the top, text on the bottom, and then it will write on page 0 the top line. So it's calling this print message. So this all here should be this 5x7. So we have the print message, the bottom line, and the print message, the top line. And then we set vertical and horizontal scrolling. This is how we do it. And there is also a multi-send, so we can send more than one command, like we have these many commands together, and we use this multi-send, and this way we can display a message to the OLED. So we have this display that is using this print message, that is using this print character, and we are using this font called the LCD 5x7 font. I'm back here on Code Composer Studio, and I'm going to create a new project. So this time I'm going to call this project the OLED button and OLED project. Let's select our debug probe. Let's select our target board, so the C505. Let's check that there is no there is this correct runtime support library. Also we will have an empty project. Okay, so it will create this folder, the workspace. Now we can extract these files from the example folder, and we are going to extract to our workspace the LED button OLED. Okay, so let's extract. So now we have here our project. Let's just check the important properties. So we need to check if the correct board is selected. We need to check if the debug probes selected. I will not use the link file now. We need to check that the memory is set to huge, and also that the runtime model options is set to 32. So everything seems to be fine. We can try to build a project to see if everything is fine. So we have here our console window. So build finished, no errors. So we can start to look what we are going to do in this example. Now we have our files here. We check the properties, and we can start our example. So in this example, it's still a audio loopback from input to output, but we will have a kind of state machine that will have 3 states. One state is no processing at all. Then we press a button, and then it goes to the next state, which is we are going to convert stereo to mono. And then we press a button and we go to the next state, which is we are going to play what's in the left input to the right output, and what's in the right input to the left output. So we are changing left to right from input to output. So we can check here our main file. We are going to use this includes, so we are including a function for converting mono to stereo. We are using push buttons. We are using the OLED. This is for future use. We're not doing a bar graph now. We're not using any DSP processing now. We will use PLL. We use the audio codec, and then the LEDs and the GPIOs and things from the USB stick 5515. Here we are defining the variables for left input, right input, left output, right output. Mono input is the same what we did in our previous example. We are going to use 48 kilohertz, so we are defining here the samples per second. Here you can adjust the gain, so if you're using a line input, you can set a very small gain or no gain at all. If you're using a guitar, you can set to 20 dB, or if you're using a microphone, you can set it to 30 dB. Here we're defining some steps, so for example we can have many different steps, and here we are defining this integer that is used to go through the samples and read and write from left and right from the audio codec. So again, it's very similar to what we did previously. We have this function to initialize the board. We set a PLL frequency of the processor. We initialize the audio codec and the I2C for the audio codec. We also initialize the 4 colored LEDs. We've seen how to do this. We've seen this function, which is the initialization of the LEDs. So we set the direction to output, and also we turn off our LEDs. This is what we're doing here. Then we are also initializing the OLED. So we've seen also this function. So we configure, we enable the I2C, we set contrast, we set the different configurations, the different voltage clocks and everything to start using the OLED. Here is for the SAR ADC, so we are going to use the push buttons, and we have this initialization. So then we are going to display an empty message. So this is the OLED display message that we've seen before, and here you can see that there's 16 characters and 16 empty characters, so it will be a blank display. Then we will print that we are running our project for the LED, the OLED, and the button. So is the audio loopback. Here I'm just displaying also some message. So it's the Guitars AI tutorial 4, and then we are waiting. So you can see, and then this is some instructions that will be placed in the console. So you can press switch 1 for down, switch 2 for up, switch 1 and 2 at the same time for reset. And we have these 3 steps. Step 1 is no processing. Step 2 is stereo to mono, and step 3 is left input to the right output and right input to the left output. Here again, we've seen that we are setting this XF LED off, and now we are going to loop through and start reading from the audio codec. Here we are converting the stereo to mono, and we are placing this into this mono input. So if we want to use this, we have this stereo to mono. So this stereo to mono is this simple function that basically we are adding the 2 channels and then dividing by 2 to prevent the overload. So now we are in step 1. We save this step to this function. It's called the push buttons read. So in this push buttons read, we give the number of steps we want to have. So this is the maximum number of steps, so we're using 3 steps, and then it will read the state of this analog input, and then it will say if it's the switch 1 was pressed, if switch 2 was pressed, or switch no switch is pressed, and then it returns this value. And we've seen before here how to do the debouncing, so this is exactly what you're doing here, and this push buttons read will give us the state. So it's not the steps, so it's not the state of the push button, but it will read and then it will give us the steps, because we can loop through. So if we're in step 1 and then we press up and then go to step 2 and then we press up and then we press up again, we'll go back to the first step. So here we are doing, if we are in step 1, so this step is the return from this function here, then we will do no processing. So here I am also setting an LED to display that we are on step 1. So for each step we have a different LED that's going to be with its light on. On step 2 here we have already the stereo to mono, so the left output and the right output gets the mono input, and here we have this OLED display, and also we set another LED, and finally we are in step 3, and then we are just changing the left output gets the right input and the right output gets the left input, and we have here this OLED display message. So step 3, left to right, right to left, and then here is the same like the previous example what we did. So basically we are using all these functionalities and components of our board that we've seen. So we are using push buttons, and we are using this way here to loop through different steps. So we can also use this push buttons read raw that will tell us which button was pressed but not which step we are in. So this is just a way to loop through steps very easily. And this is what we have now.